So hello everyone. Today we are going to see some questions of theory of computation. The first question is use the set of productions to show that each of these sentences is a valid sentence. A. The happy hare runs. B. The sleepy tortoise runs quickly. C. The tortoise passes the hare. And D. The sleepy hare passes the happy tortoise. Let's see the answer. Let's create a simple context-free grammar of productions to derive each sentence. A sentence comprises of noun phrase and verb phrase, named as NP and VP. Noun phrase consists of determinant, adjective, and noun, and verb phrase consists of verb and adverb. Now let's apply these productions to the given sentence. A. The happy hare runs. As we discussed, a sentence consists of noun phrase and verb phrase. So here the noun is here, and a noun phrase consists of determinant, adjective, and noun. So determinant is the adjective is happy, a noun is here, verb phrase is verb. There is no adverb here, and the verb is runs. The next part, B part, the sleepy tortoise runs quickly. Similarly, sentence consists of noun phrase and verb phrase. Noun phrase, noun is tortoise, and determinant is the adjective is sleepy. Here the verb phrase contains the verb and the adverb, which are run and quickly respectively. Let's move on to the next one. The tortoise passes the hare. Uh, Here the determinant is the noun is tortoise, and the verb phrase consists of the verb passes and determinant the and the noun here. The sentence is like noun phrase, verb phrase, noun phrase. D. The sleepy hare passes the happy tortoise. Here the sentence consists of noun phrase, verb phrase. Here determinant is the adjective sleepy, noun hare, verb phrase, verb passes, and again the noun phrase determinant the adjective happy, and tortoise is the noun. Question 2. Construct the derivation trees for the sentences in question 1. The derivation tree for the first sentence will be like this. The happy hare runs. Sentence, noun phrase, and intransitive verb phrase. Noun phrase consists of article, adjective, and noun. Article, which is the adjective, which is happy here, and noun is here. Intransitive verb phrase consists of only the verb, intransitive verb here, which is runs. Second one, the tortoise passes the hare, which is the sentence. This sentence consists of noun phrase, intransitive verb phrase, and noun phrase. Again, the noun phrase consists of article and noun. The article is the here, and the noun is tortoise. Intransitive verb phrase consists of intransitive verb, which is passes. There is no adverb here. Noun phrase consists of article and noun. The article is the, and the noun is here. Sleepy tortoise runs quickly, which is the sentence here. This sentence also consists of noun phrase and intransitive verb phrase. Noun phrase consists of article, adjective, and noun. The is the article here, adjective is sleepy, and noun is tortoise. Intransitive verb phrase consists of intransitive verb and adverb, which are runs in quickly respectively. Question 3. Construct a phrase structure grammar that generates all signed decimal numbers consisting of a sign either plus or minus, a non-negative integer, and a decimal fraction that is either the empty string or a decimal point followed by a positive integer where initial zeros in an integer are allowed. So here the sign as sentence is sign integer and as sign integer dot positive integer. Sign can be plus and negative. Integer is digit. Integer digit can be vary from 1 to 9 0. Positive integer is integer and non-zero digit. Positive integer, non-zero digit and integer. Positive integer is non-zero digit. Non-zero digit is 1 to 9 except 0. Give the Bacchus Norris form of this grammar. Sign decimal number equals to sign integer or sign integer dot positive integer. Sign can be positive or negative. Likewise, integer equals to digit or integer digit. Digit can vary from 0 to 9 and non-zero digit can vary from now 1 to 9 excluding 0. Positive integer can be defined as integer non-zero digit or non-zero digit integer or integer non-zero integer integer or non-zero digit. Here are the trees for sign integer. This consists of sign and integer. Sign here is negative. Integer consists of digit and integer. Digit is 1. Integer again digit and integer. Digit is 0 and integer digit 9. Sign decimal integer, which is sign negative. Integer digit 3 and 1. Positive integer is non-zero digit 4. Question 4. Give production rules in Bacchus-Naur form for an identifier if it can consist of one or more lowercase letter. The identifier equals to lowercase letter or identifier lowercase letter. Lowercase letter can be A to Z in lowercase. B. At least 3 but no more than 6 lowercase letters. Identifier equals to lowercase letter. So we're gonna start from 3 and continue up to 6 lowercase letters, and lowercase letters can be from A to Z. 1 to 6 uppercase or lowercase letters beginning with an uppercase letter. Beginning with uppercase letter, that's why UC letter, or the next can be uppercase letter and any letter. Letter defines lowercase letter or uppercase letter, and it will go from 3 to 6, and lowercase letter consists of A to Z lowercase. Uppercase letter comprises of A to Z in uppercase. D. A lowercase letter followed by a digit or an underscore followed by 3 or 4 alphanumeric characters, lowercase or uppercase and digits. Here the identifier is lowercase letter. First one is lowercase letter, second is digiters. Digiters can be identified as digit or an underscore. Alphanumeric can be identified as a letter or digit, where letter is either lowercase or uppercase. Several extensions to Bacchus-Naur form are commonly used to define phrase structure grammars. In one such extension, a question mark indicates that the symbol or group of symbols inside parentheses to its left can appear 0 or once, that it's optional. An asterisk indicates that the symbol to its left can appear 0 or more times, and a plus indicates that the symbol to its left can appear 1 or more times. These extensions are part of extended Bacchus-Naur form, and the symbol question mark, asterisk, and plus are called meta characters. In EBNF, the brackets used to denote non-terminal are usually not shown. Question 5. Give production rules in Backus-Naur form that generates all identifiers in C programming language. Can identifier starts with a letter or an underscore that is followed by one or more letters, uppercase letter, underscores, and digit. Let's see the answer. Certainly, here are the production rules in Backus-Naur form for generating identifiers along with a simple code segment as follows: identifier colon double colon equals to letter pipe identifier digit can vary from 0 to 9. Letter or digit defines letter or digit, and where letter vary from A to Z or in uppercase E to Z. And here's a simple C program segment demonstrating the use of identifiers. In this example, variable 1, mychar and float 123 are valid identifiers. Following are the rules specified in the Backus-Naur form comment line below. Include stdioh int main int variable 1 char mychar float my float 123 invalid identifier return 0. Question 6. Give production rules in extended Backus-Naur form that generate all decimal numerals consisting of an optional sign, a non-negative integer, and a decimal fraction that is either the empty string or a decimal point followed by an optional positive integer optionally preceded by some number of zeros. Here are the production rules in Backus-Naur form EBNF for generating decimal numerals. Decimal number equals to bracket sign non-negative integer decimal fraction sign can be plus and minus non-negative integers equals to 0 or digit up till 1 to 9. A decimal fraction can include a point positive integer 0. Positive integer can include digits from 1 to 9 and digits zeros include 0. Digits from 1 to 9 include 1, 2, 3, 4, 5, 6, 7, 8, 9, and digits from equals to digits 1 to 9 or 0. Here are the production rules in extended Backus-Naur form EBNF for generating decimal numerals. Explanation: decimal numeral represents the overall structure of a decimal numeral. Sign represents optional sign. Non-negative integer defines that either single zero or a sequence of digits starting from 1 to 9. Decimal fraction represents the optional decimal fractional part. Positive integer is a digit from 1 to 9 followed by additional digits. Zeros represent an optional sequence of zeros. Digit 1 to 9 is a digit from 1 to 9, and digit is a sequence of digits including 0. Example code: it's the same code that we have discussed. Question 7. Give production rules in extended Backus-Naur form for identifiers in the C programming language. Here are the production rules for identifiers in the C programming using extended Backus-Naur form EBNF. Identify equals letter, identify character. Letter can be in lower case A to Z or in uppercase A to Z. Identify character can be letter or digit. Digit can be 0 to 1, 0 to 9. In this rule, identifier represents overall structure of an identifier. Letter represents letter uppercase or lowercase, or identify character includes letter, digits, and underscores, and digit represents any digit from 0 to 9. Question 8. For each of these strings, determine whether it is generated by the grammar given for postfix notation. If it is, find the step used to regenerate the string. First string. Let's analyze the each string based on postfix notation grammar. The postfix notation grammar typically involves operand followed by operators. The order of evaluation is from left to right. The basic grammar rules are: operands are single characters. Operators include plus, minus multiplication and division. Let's analyze the given string. First string is ABC asterisk plus. Steps: put ABC onto the stack, pop C and B and perform multiplication as C asterisk. Push the result CB onto the stack, pop CB and A and perform addition CB plus operation and push the result CBA onto the stack. Result is CBA. XY plus plus. The given string XY plus plus is not generated because there are two plus symbols followed by two add operators. See XY minus Z asterisk. Steps: push XY onto the stack, pop I and X and perform y minus operation, subtraction operation. Push the result YX onto the stack, push Z onto the stack and pop Z and YX. Perform the multiplication ZY asterisk operation. Push the result ZYX onto the stack. Result ZYX. D. WXYZ minus X strict. Steps: push WXYZ onto the stack, pop Z and Y and perform subtraction ZY minus operation. Push the result ZYZ onto the stack, pop ZYZ and perform X multiplication operation and push the result XY onto the stack, pop XY and W perform division operation and push the result YW onto the stack. Result YXYW. E. EDE minus X strict. Steps: push EDE onto the stack, pop E and D, perform subtraction ED minus operation and push the result ED onto the stack, pop ED and A, perform multiplication EDA star operation. Push the result EDAA onto the stack. Result EDAA. Question 9. Use Backus-Norris form to describe the syntax of expression in Infinix notation where the set of operators and identifiers is the same as in the Backus-Norris form for postfix notation, but parentheses must surround expression being used as factors. For each of these strings, determine whether it is generated by grammar Infinix expression by it or not. If it is, find the steps used to generate the string. First, XY plus Z not generated. Second, A, B, C, D. Expression A whole can be expressed as expression and the AB and CD will be the terms and plus will add operator. Then we split the term into factors and multiple operator, factor, multiple operator, factor, add operator, factor, multiple operator, factor, and the factor will be identifiers. Identifier, multiple operator, identifier, add operator, identifier, multiple operator, identifier. Similarly, M star M plus P, expression, term, factor, multiple operator, factor, factor, multiple operator, expression. Here expression is N plus P, factor, multiple operator, term, the term is N, add operator, and again term which is P, factor, multiple operator, factor, add operator, factor, and lastly identifier, multiple operator, identifier, add operator, identifier. D. What is D? E M plus N strict P minus Q. Expression, term, factor which is M plus N, multiple operator, factor, P minus Q. Expression, M plus N, multiple operator, expression, P minus Q. Term, M, add operator, term, P, multiple operator, term, P, add operator, term, Q. factor, add operator, factor, multiply operator, factor, add operator, factor, identifier, add operator, identifier, multiply operator, identifier, add operator, identifier. Question 10. Construct FA to accept the set L of all strings over 0 1 ending with 0 1 0. Here we have to construct a finite automata. We can construct a deterministic finite automata to accept the set L of all string over the 0 1 ending with 0 1 0. Here's the breakdown. Here is the states given q0, q1, q2, q3 and well 0 1. This is the finite operator that accepts string which is ending with 0 1 0. Question 9. Construct push down automata to accept the string L of all string over 0 1 ending with 0 1 0. Push down automata defined by its these are the following rules: R1, R2, R3, R4, R5, R6 and R7. By this rule we can determine the values. Question 12. Construct a finite automata, push down automata and Turing machine to accept the set L of all strings over 0 1 ending with 0 1 0. This is the states q0, q1, q2, q3, q4, q5. Question 13. Construct a Turing machine that accepts the language 0 1 asterisk plus 1 0 asterisk. Is the Turing machine for the question and the states q0, q1, q2, q3, q4, q5, q6. Question number 14. Construct a P push down automata A equivalent to following context free grammar as OBB, BOS, 1S, G. Test whether the 0 1 0 output is in NA. Here's the answer for PDA. Thank you.